Okay, so, well, first of all, thanks for inviting me. It's a real pleasure to be here. And yeah, it's very exciting to be here because of, all that it's related to big data, machine learning revolution, right? So, for the ones that have been practitioners for more than 20 years, but also teaching students, I can tell you that we've never seen anything like it, right? Because on one side, we're now more brave to use new data that it's out there, also new models, right, that we started using, we disregarded, and now we're back using them. And I'm going to give my take on how we can use machine learning, right, our take, right? And so that's on one side. And on the training side, so this year I've been training more than 150 people on big data and machine learning, right? And it's because the old folks, including myself, needs to recycle and learn these new techniques and discuss about NLP, etc., right? And also because, the new talent is perfectly aware that now, as we were discussing with Peter, maybe instead of martingales, they should be looking at NLP, right? And this is happening as we speak, right? So I started teaching two weeks ago, and the first email I got from one of my students is listen, we did an NLP analysis of 10 Ks, 10 Qs of several companies, and we had bad results, right? And those bad results were just because we know that our classifiers are weak, right? For the ones that we've been in industry for a long time, we know everything is weak, right? So our classifiers, our regressions, just explain a little bit of the stuff, but there's a high percentage that it's not explained, right? So, and that's what Armando said, and also JP Morgan reflected on high expectations and what you get, right? So, sometimes, in all our time series analysis, and I'm going to discuss, before discussing specifically the modeling choice to go to portfolios, that we know here that it's a very challenging one too, right? Because of estimation issues and all that stuff, right? So I want to just quickly discuss how I see and how we see machine learning, what I call here the signal factory, right? So, and I have slightly different views on what to do in the presence of a huge amount of data, what to do, what are the important features and all that stuff, right? We always have a bunch of issues, right? We all know the ones that we've been practicing, and we always have maybe the one on the box, on the top box, on non-stationarity and estimation are, of course, probably our biggest enemies, right? So the fact that things might not be stationary, so the past, maybe it's not, so statistical distributions that were present in the past might not be present in the future, or are slightly different. That's always some sort of a huge challenge, right? And estimation, right? So sometimes, or many times, so the people running the algorithms on financial data is not aware of the huge implications of estimation, right? So, and we all know that if you do a mean variance optimization on raw data, the results you get corner portfolios, you get a bunch of issues, right? And to get around those issues, right, you need to do a lot of things. And we're going to see some of the things that we think make sense in order to some sort of alleviate this estimation issue, right? Okay, so this is a similar classification, right, to what J.P. Morgan showed. So fast machines there, automation, I need to be fast. HFT is clearly one of the main applications, supervised, right? On supervised, you can apply to prices, returns, and factors, right? And my first thought on this is that our experience on running machine learning models, nonlinear models, and stuff on time series is that you have let's say two possibilities. You have the multi-factor models, which you have exogenous variables that you look at, and time series, so that you try to put your machine learning models to compete to your ARMA, to your ARIMA, to your GACH, or to your econometric model, and their results are never very good, right? So even if you try LSTMs, right? Even if you try deep learning, right? And you try to use models in deep learning that have memory, right? It's always hard. The results are always very close to ARMA, for example, right? So, but still, right? So my take on this is for time series, also machine learning models struggle a little bit to capture something. Where the promise and the results are probably better is when we try to use those models in a multi-factor space, right? So trying to, and unsupervised is a typical example. So when the revolution came, so we thought, oh, how can we use unsupervised? And then after a while we said, oh yeah, but we're using it. We're PCAing everything. So we're already using PCA to improve estimation. So this idea of trying to uncover factors that might be in the data that might be nonlinear, that might be, so this is something that we've been using for already years, right? And now we're some sort of evolving to use nonlinear stuff like autoencoders, like saying, oh, why if instead of PCA we'll use nonlinear stuff in order to uncover those hidden factors, right? So, and let me draw your attention into, there's been little done in terms of seeing what PCA, what is the estimation problem on PCA, right? And we also some sort of had problems with stability of PCAs, right? Meaning that PCA also has problems into estimation. The next revolution in machine learning in finance, one of the revolutions is how do we need to tackle all the huge estimation issues that arise, right? In all the models we use, right? So estimation is an issue. Right, that's so I think you can take that home. In terms of deep learning, very quickly, because we need to move on to the portfolio allocation, right? I have some sort of the same view that yeah, well, we are the fathers of deep learning are telling us, you shouldn't be using those things if you don't have a huge amount of data. And back to the estimation issue, right? So you can't have thousands of parameters to estimate, then you're going to estimate very well. I have a different view, a little bit of a different view on this. Sometimes we just are forced to shrink. So you know that when you have little data, right, all you can do, and the statisticians tell us, all you can do is shrink, right? So try to shrink to your beliefs, or try to shrink using PCA, or why not deep learning, right? And we will know, and we know that the results are not going to be super statistically satisfying, but it's all we can do. So why not using those techniques as shrinkage? You see, so as a marginal improvement to my existing models. And you need to be very humble, right? You need to be very humble, right? Just a 2% is a win, right? And you're always going to be on a 50-ish, right? Or hopefully higher, but you're not going to be in 65-ish, right? So my students that come with 65s, I always tell them, there's a mistake, there's probably a mistake or a bug in the code because we're not used to, to have such a sunny etc., etc. Right? So anyway, so my take is, yeah, even if these things are thought to have a lot of data, you can use them carefully as shrinkage, right? The same way we're using PCA, etc. And then maybe one word on NLP before moving on, and sentiment analysis that I always need to clarify in the questions that the audience asked me related to this interpretation relevance thing. So the fact that we use sentiment analysis, that doesn't mean that we don't have interpretation issues. The machines are not solving that. So a machine can be reading an Apple, right, earnings release and think that it's positive, another machine thinking that it's negative, and then I invite you to do the same thing here. Maybe you'll interpret 50% of you positively an Apple earnings release, and the others, right, negatively. And maybe the machines need to learn that there's bears and bulls, right? And those biases is that what the machine's are going to need to learn. The fact that interpreting things, it all relates to our biases, right? Sorry for this very long introduction. Okay, now, so new models. So the first slide is about we have new models. We have to be very careful, and there's a lot of promise to them when we have nonlinearity, when we want to discover features. That is something that the audience mentioned, hugely useful. All we do when we PCA and we multifactor and we spend this huge amount of time is trying to uncover features of the data that maybe we haven't, right? And nonlinearities. And here we have the other reason that we need the machine learning revolution, which is there's such a huge amount of data that we're not able to process, the humans. So in the past we had Bloomberg, Reuters, and data feeds, and now we have all these data providers that or fantastic companies like RavenPack that have solved us the problem of, listen, I don't know NLP, I don't know how to crunch this huge amount of data, right? Let me buy that, right? And let me make sense of this. Okay, so this is the revolution. Now, let's move on to how we go from signals to portfolios. And while I know that you don't especially feel comfortable with seeing lots of equations, I'm going to skip some sort of the maths part of it, but at the same time to send you a few messages. And pretty much pretty much the portfolio allocation or the portfolio construction methods you're going to use is probably also be linked to the way you assess estimation risk in your portfolios, the way you think results coming from the backtesting are robust or not. And the previous speakers have mentioned, and it's difficult to understate the importance of robustness in all we do, right? So pretty much 70% of the messaging we do on the data is try to robustify what comes from the models, right? And just because, just a question, so something that the answer that we need to give when someone says how you deal with overfitting, why there's so much overfitting out there, etc. So part of it is because, think about this, right? So, and I'm going to just quickly explain what is this, but think about the massive amount of optimizations that you do to get your signals. How many optimizations? So maybe 3 or 4 or 5 already. Without even think about the portfolio problem, you've already tortured the data 4 or 5 times, right? Because you've optimized the universe, you've optimized, you've smoothed out the data, you've ranked, so you've tortured the data and you've been optimizing. So probably it's very likely that you're carrying a huge amount of estimation risk, right? We all know that. Right? We all know how hard it is to get those expected returns. So what Markovits told us, all you need is a vector of expected returns, a covariance matrix, and then you do a simple optimization, you get a nice portfolio, right? And we all know it's much harder than that. So partly is because, again, before you get into the S's that are the signals, so characteristics of something in a stock or a bond that might be like momentum, value, or sentiment, right? So then we have those S's, then we need the risk drivers. The risk drivers are the ingredients that you need to price your portfolios, right? So if you have stocks, it's easy, right? It's compounded returns, but the pricing, it gets more complicated. Of course, you have a portfolio of exotic options, but anyway. And then with these P&Ls derived from those signals, you get what you want, which is basically a vector of expected returns, which we call signal characteristics, okay? And from those signal characteristics, you put together portfolios. We're going to see a few approaches. As an example, well, and anyway, so some of the previous speakers have mentioned this idea of there's a huge, you'll probably, in order to, again, improve the robustness of your signals, you probably need to do, and we really encourage you to try do some sort of robustify your signals by and smoothing, right? So trying to, with exponentially weighted moving average approaches, scoring and ranking, right? So some sort of, again, try to have a smooth version of the signal instead of a very noisy signal, right? That it's difficult to. So if you want to smoothen out with this exponential weighted moving average momentum, what you get is this one. And then you can score it, and then you can rank it, right? So, and of course you can some sort of a smooth and use the signal, but we think this might be okay a good way. And let me show you examples. So we have 309 stocks. Instead here, what we use is a reversal signal, so minus momentum. So we try to look for mean reversion in these 309 stocks. And the way we process this momentum signal is smoothing, scoring, and ranking. And you'll see how that works in a portfolio. And then, as constraints, so you like to have a zero correlation constraint with the market, and that, so if you put a zero correlation constraints in your automation, you're probably pushing your portfolio to a Fama-French thing, right? Of course, the wonderful idea that Fama-French had in order to just have exposure to a signal is I long the best ranked stocks on this, and I short the ones that rank worst, and I try to isolate the momentum, the value, the growth, etc. Right? It was a wonderful idea. This one, trying to. So if you do that, the portfolio is going to be tweaked to that Fama-French version. You can also introduce constant variance constraints and dollar market neutral constraints, right? Which is also Fama-Frenching the portfolio, right? If you wish. Right, so this is what these are the results if you do that from 16 April 2010 to 15 March 2015, and see that the portfolio it has good results. Well, not surprising, is a back testing. I'm not saying that this is what you should do tomorrow, right? This is, but it's the approach that I think it might be interesting for you to explore. So if you smooth score and rank the signals, you'll get this some sort of a smooth version of the signal. Then if you calculate the characteristic, you have this some sort of also a smooth version of the expected returns, and then the dollar weights that are different from the characteristics because of the volatility, but that nicely, right, reflect that. So that's a possibility. Again, I think the idea is that you torture some sort of the signal in order to robustify the signal, right? Now, here I show the maths that are a little bit complicated, just if you want to do it with multiple signals, right? There's a paper that I can send you, right? So, and the idea is to use these multiple signals also with this no cross exposure condition, the volatility boundary condition, right? Now, so this is how we see everything we need to do, right? So, and I'm going to focus right now, and I will have a little bit of space for questions on this portfolio construction, right? So I've mentioned an approach, which is characteristic portfolio. So basically, I smooth, rank, and smooth, score, and rank the signals, and I try to put together a portfolio that carries less estimation risk, right? Still, so maybe probably this one is the. I'm going to spend more time on this one, right? So first, so then of course you're gonna raise the typical issue, which is, oh yeah, but it's very hard to get the vector expected returns, and I absolutely agree with you. So after you run your super vector machines, your ADA boost, and so you've, as I mentioned, tortured so much the data that at that time, the vector, the potential vector of expected returns that you might get, you're some sort of not super comfortable with it, right? Okay, so and here I show the typical ways that we've used that I hope that I'm sure that you're using. So what you do when there's less confidence in this vector of expected returns, right? So you don't feel like you're using it, right? So you can do something as so. Basically, the two 3 and 4, it's basically shrinkage methods in which you simply put together the signals into the portfolios or even the assets into the portfolio by not considering the vector of expected returns, by only considering risk. Hopefully because you think that risk might be some sort of something that you feel more comfortable, that something that you feel is carrying less amount of estimation risk, right? So, of course, equally weighted, obviously. So equally weighted, so one way to some sort of benchmark, so your signals against the mark is why not equally weight them and see and use that as reference, right? Okay. Now, but equally weight is not using the covariance metrics, right? It's just accounting. So then, of course, you're interested into considering how volatile is the stock, right? Then you might be, or the signal, you might think about using equal vol, right? And the fourth, which is very popular these days, of course, you can reduce parity, right? Which is you use the same marginal contribution to risk on every signal, or the marginal contribution to risk on every asset, right? So taking into consideration correlations, right? That okay. Then another option that you might be willing to explore is just again the very simple, the magic idea that Fama French had. So in order to just fully understand what is the impact, the return, etc., of a particular signal, let's do a Fama French, right? Sort of approach, long short. I'm long the assets that have better score on the signal. I'm short those stocks, right? And I think you can also use the 5, so the Fama French use of your signals to benchmark the final output of your optimization, right? We're yet not done because we all know that that there is an additional things that you can do that we all do, which is but it's probably more for relative return portfolios, we've discovered amazing ways to blend what comes from optimization, what comes from the estimation, right? That might be an equilibrium a la Black-Leaderman, right? And your views on the market. And your views can be the signals, of course, right? Okay, so we're always been using Black-Leaderman. At the beginning is a little bit hard, but it's the perfect way to blend, all your signals, signals being quants, being fundamental, etc. Right? Now, if we all learn how to tweak, some sort of the confidence and the risk aversion, all that stuff. There is a more advanced approach called relative entropy that it's still not super popular, but it will, that allows you to have, so one of the issues that has Black-Leaderman, so Black-Leaderman was a wonderful invention, I'm not, right, absolutely, right, but it's for normal distributions and it's linear views. If you're not satisfied with this normal and you might, and you want to use nonlinear views like tweaking the correlation metrics and all that stuff, you can use the relative entropy. That it's in general an interesting, but not being used because sometimes we don't feel like the non-Gaussianity of the stuff, it's a huge issue. Sometimes we don't think that the fact that it's only linear views is already good enough, right? So, but it's your choice. You can, if you have more sophisticated views on what's happening, you can use relative entropy. The crucial decision factor on the choice of these models, it's clearly estimation, right? So the amount of estimation risk that you think that your modeling is carrying, right? So that's what drives a little bit the decision on as to whether I'm using the vector of expected returns, I'm not using it, I use no vector of expected returns, not even risk with the equally weight, or I introduce risk, right? Or the sixth that I blend, right? Things that I think it's one of the most important things that we've done in quantitative finance, right? This idea of being able to blend, things properly. Okay, so thank you very much. Now
we have time for a few questions. So we have one here.
Yeah. Sorry.
Okay, fine.
Thanks very much. I think it's common for a lot of us to try to go from large data sets with many variables and try to find the ones that are most relevant, either usually through variable reduction technique like PCA that's been mentioned here and in the previous segment. And I'm wondering if you could talk a little bit about really the possibility of going in the other direction, to looking at the error terms, which let's say has 15% of the explanatory variable remaining in it, and just trying to see if there isn't more we could extract from it.
Yeah.
Sometimes the expression used is that in that error term you have the connective tissue that underlies how a lot of these variables might behave in nonlinear ways. And I'm just wondering if you could maybe talk a little bit about that. Thank you.
Yeah. So of course, whenever we're modeling our multi-factor models, so what happens with the residuals, it's a big issue, right? What happens with these U's that appear in our models, and yet we don't know if because nonlinearity is because the statistical distribution are not being Gaussian. It is because there's nonlinear relationship within the factors. So my take on this is that the only answer is that you probably need to some sort of, and that's what we all do, right? So we calculate the covariance metrics, right? And we some sort of try to estimate it better, right? And then we do PCA to try to understand better also the correlation metrics. We run the multi-factor models. Machine learning gives you the option to do some sort of nonlinear, right? Or nonlinear autoencoders, right? So nonlinear PCA called autoencoders. So basically, otherwise, right, we all know, and just by looking at the Fama-French papers, you realize how intricate the life of 5 factors can be, right? And the last paper that it's wonderful, it has an AQR answer, like, yeah, but if you take away this one, you tweak a little bit this one, and you add one, then value is again, right? So we don't have the answer to other than a huge combinatorial problem on what is the best way to combine factors linearly, nonlinear, but I seriously advise to, as usual, throw all the statistical things that we have, and then, as Marco mentioned, is the art part of it, right? So statistics is also science and art, right? So the part of it is interpret results and see how we live with this 53%, 52, 50-ish explanatory power, right? So that's why our life is so hard and so interesting, by the way.
Thank you, Miquel. We're quite short on time now, but I want to thank Miquel for his great presentation. Thanks a lot.
Thank you.
This is RavenPack.